talk about should be very familiar to you. So Newton's third law basically says what? We refer to this law as the, when we write it this way, we say the F of force on 1 on 2 is equal to the force of 2, the negative force of 2 on 1, okay? So if you look at the foot being A and the ball being B, okay, you can see that they are equal in magnitude but opposite in direction, okay? Equal in magnitude and opposite in direction. We typically call this the action-reaction law. With every force applied to an object, the second object applies an equal but opposite force on the first, okay? It's typically, if you want a textbook definition, there it is, all right? So if we apply forces, and all of you have done this, and again, this is one that's a little bit harder to wrap our brain around because it does not appear that there is a force being applied. Let me see something I can do. Typically, everybody says push on the wall and the wall pushes back, right? Well, that's a little bit hard conceptually to understand because we really don't see the wall pushing back, do we? Okay? We really don't see it. Now, next week when we do Newton's third law, it's going to be pretty obvious when we use these force sensors, and it's a fairly simple lab, but it demonstrates Newton's third law perfectly, that there is actually an opposite force. And whatever force you pull on that object, that force pulls back with the same force in the opposite direction. So a lot of times we say, well, push on the wall. Well, that's not a really good demonstration, I guess you could say, because it's hard to see. The wall's not, we don't see it moving backwards, but we know that all the mortar in the joints and on the floor, and of course the weight of the blocks, the normal force of the blocks, all comes into consideration of assisting or causing, I should say, the force in the opposite direction. Now we know, why does it not fall? Or why do I not fall? Okay. Well, we know it's not going to fall because I don't have a net force applied to it. Now, if I bring a bulldozer in here, big Caterpillar 10, it's going to fall, all right, because the Cat 10 has a much greater force. I guess you could say, look at it in terms of work. It has net work, okay? We'll get to that chapter 6, okay? But, again, every time you kick a ball, why does a ball, if your foot goes this way, the ball goes in the same direction, does it? Well, sure it does. But you got to realize right here at the point of contact, the force is in the opposite direction, okay? And remember, we're talking about at point of contact, okay? We're not talking about necessarily the force that the ball may have of its own due to its weight. We're not talking about that. We're just talking about right there at the point of contact. If a bug flies into a windshield, which applies a greater force, the car or the bug? At the point of contact, it's equal, okay? All right. Okay. Believe it or not, it really is. All right. Okay, it really, really is. Okay. And that's Newton's third law. And of course, mathematically, that's how we write it right there. There's your equation for Newton's third law. Okay. And if you want to do A and B, F of A on B is equal to the negative F of B on A. Okay, you want to write it that way. Okay. And that's it. That's Newton's third law. Very simple. Okay. And like I said, when we do lab next week, today we're doing second law. Next week we're doing third law. We will eventually get to air, probably do the air resistance a little later on. But anyway, that is Newton's third law. Okay? Any questions? All right. You know, we talked about, last week we talked about being in space, working in space. Many times we attribute momentum comes into play here with Newton's third law, and torque, okay, when we look at Newton's third law. However, torque goes a little bit further. We have to look at center of mass, okay, and the pivot arm, okay, and we'll look at that towards the end of the semester. But it is related to Newton's third law. Remember, we talked about working on a satellite or an object in space, in orbit. Remember, you don't just yank that wrench. You don't just jerk it real fast, okay? Why? Well, because the force you apply to that wrench, you're in free fall, you're in microgravity, you're floating. You got to realize that when you pull on that wrench is going to pull back on you. Okay, so if you jerk it with a very high amount of force, then guess what? There's a force pulling back on you, okay? And you've got to realize that while you're working in space. Like I said, that's why they work on things in these deep water pools. NASA's got one up at Marshall Space Flight Center, where the astronauts get in that pool and they get all their regalia on, and they work on simulators to simulate their motions, to simulate the forces they're going to have to be dealing with. Because all of you know, if you're floating in a pool, how hard is it to try to move something? It's really hard, isn't it? If you ever wrestle with someone in the pool and your feet's not on the bottom, it's pretty hard, isn't it? It's kind of hard for one or the other to get the upper hand, okay? And that's why they always do those simulations, the astronauts do, in those deep water pools, okay? Because that's the best way to simulate Newton's third law, okay? Okay, all right, okay? Okay, so now let's look at, let me stop. Oh, don't do this to me. Why I did that, but anyway, and why does it do that? How do you turn that off? I need to turn that off. It gets on my nerves. I don't know who turned it on. I didn't, but there it is. All right, so let's stop really quick, and let's pull up another one.